So welcome. So we're going to talk about interference of light waves. And so we know that light is sometimes thought of as a particle, and it works very well like that. And light is also sometimes thought of as a wave, and it works very well like that. And so far we've been dealing with light as a particle, and it travels in straight lines, and we can do geometrical optics on it. But now let's look at some of the wave properties. And some of these have been known for quite a long time. So to see interference effects very clearly, then we need to see a couple of things. I've got to go down here and get my pen. So we need to see that a source must be coherent. And by coherent, sorry, I'm having just a bit of trouble here. By coherent, we mean that the waves are in sync with each other. So, for example, that's right, it is here. So, for example, if I look here, I can see that these waves are in sync with each other because the maximum where the crest is, and the crest is there, and the crest is there, they line up. So that lines up with that, and the one along here lines up with there, and the one down here, and the one down there, and then the one down here, and the one there lines up with there, and the one there, and so on. So even though they're different photons entirely, they still reference to each other. It's like if we had a continuous wave, we'd expect a crest and a crest and a crest and a crest and a crest. We'd expect it to, like soldiers marching, would be in step with each other. We'd expect that for a continuous laser beam, for example. Well, these photons can be in step with each other, even though they're individual photons, as long as they've been produced by a coherent source. And a laser is the most, well-known coherent sourse. But this work was done a long time before lasers, which raises the issue of how on earth could they do it. Monochromatic simply means a single color. So you have to have, 400 nanometer light. Now, frankly, what happens is when you get into this, you start saying, well, hold on. Is 400 nanometer light different from 401 nanometers? If we have those mixed together, will it be a problem or will it not be a problem? And you find that when we say monochromatic, we don't mean perfectly monochromatic because there's no such thing. We mean about a certain value, one shade of red, not red, green, and blue mixed in together. We mean that. And then they must obey the superposition principle. And all that means is that if I get a crest coinciding with a crest, they add together. I get a crest that's twice as big. And if I have a trough corresponding to a trough, they add together. And if the crest arrives when a trough arrives, they cancel each other out. Just means that you apply just normal arithmetic math to it when you're figuring out what's going on. Okay, so we have a normal light source. Nothing special, just an incandescent light bulb, a filament light bulb. And that's not coherent. Those photons just haphazardly arranged. They go in all directions at all times, all phases. So how on earth can we get that first law met? And it's very interesting. Basically, remember what we said about a wave coming and then having an opening, and if the opening was, less than the wavelength of the wave, you tended to get this thing where the opening acted like a point source of energy. Same thing happens here. We get this thing where it's like a point source of energy. So what happens is, because this is in between the two slits, what happens is we get the crest appears at one slit when the crest appears at the other slit, and the trough appears with the trough. So it becomes coherent. Whether he knew that's what he was doing or not, I don't know. I suspect he did, but he probably wouldn't use the same language that we used. But either way, he used a very sophisticated source, really. He had two openings. And if he had shown one opening, he would have got a kind of brightness that looked like that. It would have been bright in the middle and darker on the edges. Either one of these would have given that. But when you open up both of them, you get this guy in the middle. And it really is quite shocking. You get these little dark fringes. And there's nothing between that fringe and either one of those slit openings. There's nothing to block the light. As I say, if you cover one of them over, you get light. So getting rid of an opening gives you light. Getting rid of the other opening gives you light, but you have them both uncovered and you get these fringes. So a bit of language first of all. These are called fringes, and we have light fringes and dark fringes. And what we see is two slits act as a pair of coherent light sources. We get a pattern of dark and light fringes that depend upon the difference of the point's distance from each of the two slits. So it's a path difference effect, just like we talked about in oscillations and waves, when we had the two speakers and they were sometimes in phase and sometimes out of phase. And it's going to be the same rules. We identify the fringe by its order, that's terminology, and we assign a value of m to it. It's the same rules we had before. If the path difference is an even number of half wavelengths, we get constructive interference, which gives us a brightness. And if the path difference is an odd number of half wavelengths, we get destructive interference, which gives us a darkness. Just like with the speakers. Now, we need to do some terminology naming here, and this is where it gets confusing. So we have the 0th order. First of all, break this diagram in two, because it's symmetrical, going up and going down. Okay? And starting on the middle bright fringe, it's a 0th order bright fringe, and its m value is 0. Go to the next fringe out, the darkness. That's the 0th order dark fringe, and its m value is a half. And then we get the 1st order bright fringe and the 1st order dark fringe. And then we get the 2nd order bright fringe and the 2nd order dark fringe. And we can go on like that. 5th order bright fringe, 5th order dark fringe. So they go bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, dark fringe to work our way out. And the way it goes is all the bright fringes, because they have to be an even number of half wavelengths, path difference, they have an m value of 1, which is 2 halves, or 2 4 halves, 3 6 halves, 4 8 halves. It's an even number of halves. 0 being no halves, which is even. And the dark fringes, well, there's 1 half fringe, and then 3 halves, and then 5 halves, and then 7 halves. So you need to know that terminology. Don't fall out because of that terminology. Be able to look at this fringe and figure out what the order is, what the m is. In the book, they use 2 different equations, one for the bright fringes and one for the dark fringes, and it drives me crazy. Because they only have m equals the whole number, and then they add a half onto it in one case, and they don't add a half onto it in the other case. And I just think that's a waste of time. Just learn the m value for the appropriate fringe, and then you're on your way. We'll get to the equation in a minute. Okay?
So, what's coherent again?
Coherent means that the waves have their crests at the same point in time.
Oh, can you match up?
Match up. Like with the speakers, they were coherent because they pushed together and pulled together. we said they were in phase. That for sound is coherence for light.
So in phase means coherent, or coherent means in phase?
Yeah, yeah, yeah. Okay. So Young's double slit fringe pattern. What is the M value for the third order fringe? I don't know if you got a, probably no one got one, so it's haphazard at the minute, so I'll just do these. So Young's double slit fringe pattern, what is the M value for the third order dark fringe? Remember, it goes brightness, darkness, there's your first order. There's your zeroth order. Brightness, darkness, there's your first order. Brightness, darkness, brightness, darkness. I need to do that again. Brightness, darkness, there's your zeroth. Brightness, darkness, there's your first, second, third. And they want the third order dark fringe. So let's have a look. I'm out here, and that's the one I'm interested in. And this went 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, and I prefer to write 3.5 as 7/2. So there's my value. So there's a little bit of bookwork there, but that's all it is. So starting with that, let's go back and look at the diagram. Starting with the middle, we had the 0th order, and then we had 1/2. That was your 0th, bright and dark. Then we have 1 and 1.5. That's your first order. Then you have 2 and 2.5. That's your second order. 3 and 3.5 would be your third. 4 and 4.5 would be your fourth. Yeah. Cool. So that's what I'm carrying around in my head. And then in Young's double slit fringe pattern, what is the M value for the second order bright fringe? So we have bright, dark, that's your 0th. Bright, dark, that's your first. Bright, dark, that's your second. And it's a second order bright fringe, which is that guy. So we go 0, 1/2, 2/2 or 1, 3/2, 4/2. That guy. Cool. You see that? It's the 0, 1/2, 1 and 1, 1.5, 2, which is 4/2. Yep. Cool. That's a skill that you need. Because we're about to get the equation. So just before we get to the equation, so we have path difference 0, so the paths coming from both sides. Equidistant, my point of interest is equidistant. It's path difference of 0, even number of half wavelengths, constructive interference gives me a bright fringe. And then we have a path difference. Path difference is an odd number of half wavelengths, we get a dark fringe. Even number of half wavelengths, bright fringe. So just doesn't matter if it's above or below the middle point, we're just looking for that geometry. Let's do a bit of math. I'm imagining these two rays, one going from the top and one going from the bottom. But my screen is so far away that these two lines, these two rays, on the scale I'm talking about, appear to be parallel to each other. It makes the math easier. They're not. They've got to overlap at some point, but let's draw them on this scale as if they're parallel to each other. It just makes the math easier. Because what that enables me to do is to say, so here's a diagram of the entire system, and that angle there between the straight through and whatever fringe I'm looking at. So here are your fringes, bright fringe, dark, bright, dark, whatever, yeah? Here's my fringes on the screen, just like back here. Here's my screen. I'm not going to draw that pattern again. I'm just going to draw this kind of same pattern like that. And that angle there, theta, is the same as that angle there, theta, which, because I've done parallel rays, is the same as that angle there. My path difference is effectively this bit there. Now, I know if they're parallel, they won't hit the same point, but we're imagining that it's so close to parallel, they'll eventually hit the same point. So okay, so here's my path difference. And this is D. That's the distance from the center of one slit to the center of the other slit. And I know that, or I'm given that, or I've got to find that out. I want to express my path difference in terms of the other parameters. And what I say is my path difference, this delta, is equal to my R2, distance from this slit to the screen, minus R1, which equals, now if I look at this triangle, this is an opposite to that angle, and this is a hypotenuse to that angle. So this is d sine theta. So that comes out of this geometry. So I say my path difference, which is equal to d sine theta. And then I say, well, hold on, this path difference, if it's an odd number of half wavelengths, it's destructive. It's an even number of half wavelengths, it's constructive. Oh, that's m lambda. M being 0, a half, 2 halves, 3 halves, 4 halves. So there's my equation. That's a real take-home equation. That equation we'll use over and, well, it'll certainly be on your test. So for constructive interference, you get brightnesses, constructive interference, when m equal to half or 1 or 2 or 3. I prefer to put it in 2 half wavelengths, 4 half wavelengths, 6 half wavelengths, an even number of half wavelengths. And we get destructive interference when it was an odd number of half wavelengths, which was 1 half or 3 halves or 5 halves. Cool? So before I started doing the videos, I was getting a bit frustrated because when I looked at people's notes, they'd make a mistake when I was writing something down. Or sometimes I'd make a mistake when I was writing something down. And so I decided that I was going to fill in some of these blanks. And now I don't like it so much because I just sit here and read. And it's actually much more fun for me to actually explain. And every time I explain it slightly differently. And sometimes I walk away and said, that went really well. I must remember that. Another time I said, well, that didn't work so well, so I'll forget it. But when I'm just reading, it's like I don't need to be here, you know. But anyway, so I'm going to live with it. I might get rid of them this semester. I'm just a bit unhappy with them. So here's my basic same diagram. And my question says, consider this young slit apparatus. The two slits are separated by 500 nanometers. Just by the way, any idea how big that is in atomic layers? Atomic layer is about 2 angstroms. So we get about 5 atomic layers to the nanometer. So 500 nanometers would be about 2,500 atomic layers. It's not that many when you think about it. That's like 5 reams of paper on the atomic scale. You know, it's like it's not that big a distance. So these are relatively close together. 100 nanometer light is instant on the slits. So we've got 100 nanometer light coming in like that, you know, like that. And then we get this effect. And it says, what is the angle between the second order bright fringe? We have our bright, that's our zeroth. We have our bright, that's our second order bright fringe, make to the optical axis. So now I'm over here. Here's my 2 slits. Here's my straight through, m equals 0. We had m equals 1, that's your first order bright fringe. M equals 2, that's your second order bright fringe. So m equals 2. And what we say is m lambda equals d sine theta. There's my principle. There's my basic equation. M is 2 in this case. Lambda's 100. 100. I'm going to leave it in nanometers. Okay? I'm not going to worry about changing it because as long as I stay in meters, I'm dealing with ratios to get an angle, so I can get away with it. D is 500, and then sine the angle. So my sine my angle equals, there's a little bit missed out, 200, 200 over 500, which is 0.4. And then theta equals sine to the minus 1 is 0.4, which is 23.6 degrees. If you happen to be working in radians, you just put down your answer, whatever it works out to be, in radians. Doesn't matter. They're just a unit. As long as you write down the right unit for the right numerical value, it's a correct answer. So not so bad. There's a little wrinkle. And again, it's just my way, but the book. So the next obvious question is, well, how far is that on a screen? You know, you can say what the angle is, but I want to know how far is that? What is that value? Is it 5 meters or is it 5 millimeters? What is that? Well, it depends on how big my screen is. So there's my L. And if I look at my bottom diagram, I see that, well, tangent of theta is equal to y over L, opposite over adjacent, yeah? Now, the book uses there's a little cheat in a way, and it uses a small angle approximation. And the trick it uses is it says, well, look, the sine is the opposite over the hypotenuse, and the tangent is the opposite over the adjacent. And if you're a long, long way away, then the hypotenuse and the adjacent have nearly got the same length. So we'll say that for small angles, sine theta is the same as tangent theta. It's true for small angles. But then we come to the test. And in the test, I'm giving you numbers that work out. So we end up with angles like 23.6 degrees, which is not a small angle. And then people will apply the small angle approximation to it because that's what it says in the book, and used to say in my notes. But it's very inappropriate. And so when you think about it, you don't need the small angle approximation. All you need to do is say, oh, look, that's a tangent. You know, tangent equals y over L. I know L, I want y. So y is equal to L, which is 3 times the tangent of the angle, and you get a number. So if you look in the book, it'll give you with a small angle approximation, and my advice is you don't need it. Just work out the trig. You know the trig really well. You don't need to worry about that. But anyway, you can work out the actual numerical distance on there. Okay? Yeah.
So the 100 is just from the 500 minus 400? Or,
The one.
oh, wait, no. Your thing is phrased differently.
Oh, is it different?
See, I was looking, it says here, it's separated by 500 nanometers and then 400 nanometers of light.
Oh, I'm so sorry. Do I have a different version now?
The same, just on ours instead of 100 it says 400.
That's a mistake then. Yeah, I'm so sorry about that. I need to clean that out.
Last set of practice exercises either.
Sorry?
My printout doesn't have the last set of practice exercises.
It doesn't have these.
No,
Multiple choice ones.
Doesn't have those. Those. I'm so sorry. I'll get rid of. I'll check the last few anyway to make sure they're okay. Because, you know. Do you want to know something weird? And that is, so this is because of interference, right? So the two photons, you know, the photon going on the top track interferes with the photon going on the bottom track, and if the path difference is such. Well, okay, you turn the light down, and then you sit and you calculate how long it takes a photon to go from a lamp to the screen when the distance is only 3 meters, and you find it's an incredibly short amount of time. And if you turn the intensity of the light down so you get fewer and fewer photons, you can quite easily get to the stage where you only have one photon existing at any time. Because it's there, it's there, it's there, it's there. You hear a drum beat, only one stick hits the skin at any time. But you hear the roll really nicely. You don't go, what's that? Oh, it's a drum beat. Oh, that's another drum beat. You compare and contrast, and you can see the pattern. You can see, maybe not see, but you can certainly record on film the effect. Your eye's got a persistence, you know. So, how can you get interference between two things when one of them dies before the other one's even been born? I hate to put, you know, what is it, personification on photons, but, you know, it's weird. It's just... Now, there is a sense which is that we can't think of it as particles at this point. We've got to think of it as just this wave, and the wave kind of goes through both at once and all that. That's fair enough. You can say you can't apply photons to this, but photons exist, and, you know, it's kind of like we can think of it as a continuous wave and think of it as a particle, but why can't we think of it as a particle in this case? It raises a whole bunch of very uncomfortable issues. And this is not the beginning, but this is part of where physics either becomes interesting or becomes weird, depending on your perspective. It can be a little bit... this is part of modern physics. And as I say, I find some bits of modern physics fascinating. I find other bits just uncomfortable because they just don't seem to make sense. And the answers, the solutions to the problems are just very challenging. Not even mathematically, just challenging in terms of believability, you know. There's two very good books if you're at all interested in this. Has anybody heard of In Search of Schrodinger's Cat? So you know who Schrodinger was? Schrodinger's equation, wave equation. When they went from spectroscopy, and this is part of spectroscopy, when they went from spectroscopy and started looking at, it led on to quantum mechanics. Energy states are allowed or not allowed. They started getting answers which are less and less intuitively believable. There's this sort of famous joke about some scientist was talking to Albert Einstein, and Albert Einstein said, basically, I reckon there's only 3 people in the world that understand quantum mechanics. There's this long silence. And then the guy who was talking to Einstein said, who's the third? Rather than who's the other 2, you know. We're both included, so who's the third, you know. And then I think it was somebody else. There's a guy, Murray Gell, it might have been him, who said, anybody who tells you they understand quantum mechanics is lying, you know. It's like it's something you do, and you get the answer primarily from math. Then you say, what the heck does this mean? And then you find some physical significance, and you go out and you check it, and it's right. And you go, this is like craziness, you know. It's like having the magic decoder ring and it works, you know. It's like, how does it work? I have no idea, but look, it works. So some people love it and some people hate it. I find it's one of those things where the problem is, in fact, I'm going to stop here because it's, well, I'll go on anyway. The problem is that to really get it, you've got to, there's no half measures. You'll watch programs and they'll talk about it, but they won't explain it. They'll say, well, now we're going to explain so-and-so, and they don't. They talk about it. It's one of those things where it's like you got to do the thing to get the thing. You can't really do half of it. And so some people love it and some people hate it. But there's a couple of books that are worth, if you're interested, a couple of books that are way in. And one is called In Search of Schrodinger's Cat. And the other one is called, it's a follow-up book, which is called In Search of Schrodinger's Kittens, which is the more modern version. And they're basically attempts to put this kind of science in accessible language. So you don't need the higher math to get an appreciation. But I got to tell you, you know, it's still like it's talking about it unless you sit down with the math. You know, you like sat on the sidelines. When I first started doing, I had to teach some stuff on astronomy, and you get involved in cosmology, and the same kind of thing happens. And they come up with some amazingly weird stuff, and you go, that can't be true. And finally, online, I looked up some graduate classes in cosmology to figure out what's going on. And it's couched in math. It is, and I came away with the impression that it's not that they're making this stuff up. They believe it wholeheartedly, and they have a lot of confidence in it because it comes from the mathematics of the situation. But it does come from the mathematics of the situation. You can't just draw a diagram like I like to do and say, so the answer's 27. You know, it's like it comes out of kind of like obscure math, and then you interpret that and get an answer. So some people find this wonderful and exciting, and other people say, oh, man. But you get weird stuff sometimes. Cool. Okay, let's go on to the next bit, which is I want you to recall something. Remember how when we have a wave, we're in the swimming pool and we cause a wave, the wave goes to the wall and it rides up the wall and comes back. So what goes as a crest comes back as a crest. So this is like being at the swimming pool. But I think I told you I had a waterbed for a while, and when you push something as a crest on the waterbed, it came back as a trough. It was like a really weird thing to look at. And we can do the same thing with string. If we take a piece of string and we tie it to a post, then if we flick it upwards, what comes back is a downwards flick. And if we have a loosely connected piece of string, what goes as a crest comes back as a crest. And I think I showed you on the PHET site, remember that site with the simulations? Well, there's a simulation there where you could play with it, yeah? So we don't really care about string, but we do care about light reflecting from things. So this is where we get the payback for that. Consider a traveling wave that encounters a change in the medium. Maybe it goes from air to glass, or maybe from water to glass, or glass to diamond, or glass to air or something. We get reflection, and we'll get a reflection whenever there's an interface. So if the reflecting medium has a bigger N, so diamond versus air. The one I remember is a glass, a pane of glass. So I have air, and then I have the front surface of the glass, and then I have the back surface of the glass and air behind it. So what I envisage is I envisage air, glass, air. And I know that that n equals 1. I know that n equals, I'm going to say 1.5, doesn't matter. I'm going to say that n equals 1. So when the reflection is off this front surface, I'm reflecting off a medium which is denser. If reflecting medium has a bigger n, the wave is reflected antiphase. So what goes as a crest comes back as a trough. And that same ray of light goes in here and reflects off the back wall. And now it's reflecting off something with a lower refractive index. See, it's going from 1.5 down to 1. Went from 1 up to 1.5. Now we're looking at the back face of it. So now we're reflecting off this interface, and that's a 1.5 interface going to 1. So that means what goes as a crest comes back as a crest. So there's a phase jump from the front face of the glass, but not a phase jump from the back face of the glass. So picture yourself outside a window, a big thick shop glass window, and you see two reflections of yourself. The one from the front is out of phase from the one at the back. You get a phase jump of half a wavelength in the front reflection, and you don't get a phase jump of half a wavelength in the back reflection. So there's a difference between them. They don't look any different. You can't tell, but it's there. So here's a piece of glass. We're calling it the film. And we're going to assume, well, we say that the N for the air is less than the air for the film. So this is the shop glass. Light comes in, bounces off the front, goes into my eye, and that is half a wavelength, either ahead or behind, it doesn't matter. Just half a wavelength different. What came as a crest got reflected as a trough. The reflection from the back is reflecting off a low N value medium. No phase jump. So, these two guys go into my eye. And they interfere. I'd like to know whether they interfere constructively or destructively. Oh, you say. You've got to look at the wave, at the path difference. Path difference is here. It's basically in and out. But you have to also take into account this phase jump effect. It's no longer just path difference. When there's no jumping ahead or jumping behind, it's just a path difference effect. But now we have to take into account the reflection effect. Okay? Is that clear? We've got a path difference. Clearly you can see the path difference. If that path difference is an odd number of half wavelengths, I would expect destructive interference. If that path difference is an even number of half wavelengths, I would expect constructive interference. Yeah? But there's a complicating factor here. Because one of those rays that I'm looking at had this phase jump on it, and the other one did not. So it switches things around. If the path difference is an odd number of half wavelengths, and I have this phased jump, now I got an even number of half wavelengths, so it's constructive. And if this path difference is an even number of half wavelengths, but I also have this phase jump effect, Now it's an odd number of half wavelengths, so I get destructive. I'd like to be able to do some calculations on this because I can use light then as a ruler. I'm going to jump ahead one slide or two slides. If I look at something like this, I've got this light coming in. It's the path difference is here. And sometimes the effect, path difference, and if there's a phase jump on reflection, sometimes I will get destructive interference, and sometimes I'll get constructive interference. So as I look along here, as I'm looking at different places down there, I'm seeing these lines. Now here's the thing. I can interpret that distance there as being a certain difference in height because I'm measuring path difference. So I can begin measuring distances in terms of the wavelength of light, which can be really small. So I can use light as a ruler using this technique. It's really incredibly good. And I can use it for stuff like this. Is actually this is a picture I took in here actually on that machine using a lens and a flat plate, and you can see that I have a spot in the middle, and then I have a fair distance to the next dark fringe, and then less of a distance and less of a distance and less of a distance, and that's indicative of something that's getting curvier and curvier. And what this shows me is it's a very symmetrical lens actually. It's nice pretty much in all. There's a little bit of something going on. It seems to me it's a little bit elongated in that direction, but that could have been the way it was laid or something, you know. But this is doing precision measurement using light. So this is a really useful thing. So how do we do it? And then the other thing is that you will sometimes see, we don't see it so much in Florida. It's partly because the engines have got so much better. But if you've been around engines, there's oil often everywhere. And on the pavement floor, you get these iridescent splotches of colour. And that's oil that's dropped onto the floor. And it's formed a thin film. A thin film like this. And what's going on is the oil has different thicknesses depending on where it is. It's kind of doing that on the pavement. And so by the edges it's not very thick, and by the middle it's kind of quite thick, or it's something like that. Now, we've been talking about bright fringes and dark fringes, but that was for monochromatic light. Now we have white light. It's got a whole bunch of different colours. You don't notice the dark fringes, you notice the bright fringes because they're brightness. And as you get different thicknesses, you get different colours of light promoted. And so we see these pattern of colours that basically go through, and each colour corresponds to a different thickness. And they can repeat. You can get blue in the middle, and then blue again, and then blue again, and blue again as you go through different wavelengths. But it's the same principle. I used to make metal insulator, metal electronic components. They were like incredibly thin capacitors. They were actually originally designed because they had electronic switching properties. They were like diodes before diodes became really reliable. And they were replaced by diodes because diodes were just so much better at doing the job than these things were. To study them, we'd have films of various thickness, and you'd have to monitor. You'd want to know the thickness to within a few atomic layers. And you'd have a little crystal oscillator would tell you what thickness was, and you'd stop when you were supposed to stop growing, and then you'd move on. But you could look at them. When you took a batch out from the machine, you could look at them, and if they were the right thickness, they would have the right color. It wouldn't be a vivid color. It would be like a faint greenish color or a faint bluish color. And you could basically, oh, that's 500 angstroms. Oh, that's 2,000 angstroms. You could tell by that. So this is a very practical thing. So we need to work this out. So what we say is we see vivid colors when light shines on thin films, and these are caused by interference. There is a phase shift of 180 degrees or lambda over 2 upon reflection. If the reflection medium has a higher refractive index than the medium for which the wave is traveling. We talked about both of those. The thing we didn't talk about is the wavelength in here is not the same as the wavelength out here. Remember what we said? We get slowing of light because the wavelength changes in the medium. So we better be careful we're using the right wavelength. The question's going to give you the wavelength out here, but you're going to have to deal with the wavelength in there. So we need this, the lambda at a given refractive index is equal to the lambda in vacuum over the refractive index. So we're going to take that into account as well. Yes?
So, like, with this diagram, it's like the light's bouncing off the film and you're seeing that, but you're also seeing the mixture with it when it goes through the film.
And bounces off the bottom side.
And also the third one when it comes out the bottom.
Goes away.
Oh, because there's like a little purple slit up in the...
Oh, that's bad penmanship on
Oh,
my
okay.
part.
So
Oh, I'm so sorry, no.
No, that's fine.
Yeah,
So
no.
you don't see that
That's
bottom.
bad. Yeah, don't see that bottom one.
That applies to pretty much anything, though, right? Not just thin film. Any surface that you look at, you'll see like different, I guess, the way light's bouncing off. Even though specifically this is for film, like, you can apply that to table, right?
Would you have 2 layers? If you had a polish on a table, perhaps, but then you're back to a thin film.
Oh, you would just call that, that's just the blanket term for all of it, thin film?
If there's a transparent medium,
Oh, okay.
Yeah.
I see what you're saying.
yeah. But if I had a stainless steel top, then you wouldn't have a thin film. Unless there was grease on it.
Yeah, okay then. Like, for example, your table, it'd just be like,
It's,
it would just be like one
yeah.
thing bouncing off it.
But if I get oil and spread it, you can see it. You can see fingerprints.
Yeah,
That's kind of what you're seeing. You're seeing this interference effect.
yeah,
With the
just to
finger.
a lesser degree.
Yeah.
Okay.
So then let's do one of these. And again, I apologize. I've done it, so it's like I'm cheating. But so we have a 300 nanometer light is instant upon a soap bubble. So why do we use a soap bubble? Because it's an everyday thing that everybody's seen. But we're only using monochromatic light. It's like we take a soap bubble and we put it in a room and we only have one color light shining on it. How thick a film will cause the second order brightness. Oh, this is... And I tell you, the N for the soap bubble is 1.6, and I expect you to know that the N for air is 1. Okay? So here's my diagram. N equals 1 in the air outside the soap bubble, N equals 1.6 inside the soap film, and N equals 1 inside the bubble. Yeah? Actually, inside the bubble. It's still air. So it goes air, film, air. What we say is, and then we have the layers come back, and we have ray 1 and ray 2 are going to interfere. These guys are going to interfere. And we don't worry about the angle. When I first saw this, I thought, oh, you've got to worry about the angle. But we don't. We just say, just take the thickness as being T. This path difference, This path difference here is 2t. You go in by t and you come out by t. Don't worry about the angle. I'm just drawing the angle so you can see it. Don't worry about that slight angle there. Just it goes in and comes out. That's all I care about. Yeah? So, I say, sir, a second order brightness, I've got constructive interference. So I need, in terms of, well, if we had no phase effect, if it was just path difference, I'd need two wavelengths. No wavelength difference, path difference of 0, brightness. Path difference of 1, first order brightness. Path difference of 2, second order brightness, yeah? But this is caused by two effects. We still need the second order brightness. We still need a wavelength difference of 2, but it's given us by two ways. One is there a phase shift? Maybe there is, maybe there isn't. And the other is path difference. We've got to take both of these into account. So the first thing I say is there a phase shift? And looking at this, there is a phase shift. I will get a phase shift of a half a wavelength at the front surface, and I will not get a phase shift at the back surface. So there's a difference of half a wavelength. Agreed. Let's compare that. I'm going to do air, water, that's what soap is, air. That's the one above. I'm going to do air, water, diamond. Now let's do that same argument. Is there a phase shift when my light bounces off, goes through air and bounces off water? Yes. Is there a phase shift when my wave goes through water and bounces off diamond? So in this case, I have a phase shift at the top and a phase shift at the bottom. They're both phase shifted, so they cancel each other out. The phase shift only matters when it occurs in one and not the other. So in this top one, there was a phase shift at the top, but not one at the bottom. In this next one, there is one at the top, but there's also one at the bottom. Let's reverse things. Let's do diamond. Let's do water. Let's do air. Is there one at the top? No, because I'm going through diamond and I'm reflecting off water, which is lower N. Is there one at the bottom? I'm going through water and reflecting off air. No. Last one. Water, air, water. I know that's improbable, but is there a phase shift when I go through water and reflect off air? No. Is there one where if I go through air and reflect off water? Yes. So here again, there's one phase shift, so it counts. In the first example, there was one phase shift, so it counted. In the middle one, in the second example, there were two phase shifts, so they cancelled each other out. In the third one, there were no phase shifts, so I didn't care about it. Okay? So you're looking for, is there a phase shift at one but not the other? Don't care which one. But is there a phase shift at one but not the other? So I'm looking for low N, high N, low N, or high N, low N, high N. They don't have to be the same values, but they just have to step like that. Yeah, they don't have to be, it doesn't have to be symmetrical of air, water, air. I could have air, diamond, oil. I'm still going up and coming down. So phase shift. There is a phase shift of half a wavelength at the interface A, but not at B, so there is a half a wavelength phase jump. I've got to take that into account. I want a 2 lambda effect. I got half wavelength in the bank already. That leaves 1.5 wavelengths. So this leaves 3/2 wavelengths from the film thickness. 2t, that's my film thickness 2t, because they go in and come out, is equal to 3/2 lambda. But lambda inside the film is not the same as lambda in air. Remember, lambda film equals lambda over n. So 2t equals 3/2 lambda over n. T is equal to 3 lambda over 2n, and I got the 2 down there because I've rearranged it. 3 lambda over 4n is equal to that, and there's my answer. Yeah. So 3 steps basically. Is there a phase jump? What do I want? Is there a phase jump? The rest comes from path difference. Make sure you're using the right lambda. Boom, boom, boom. Yes?
So you subtracted half a wavelength from the original 2.
Because I needed 2 for constructive interference, second order brightness. And then I took the half a wavelength away because of the path difference, because of the phase jump, and the rest was path difference, but it has to be the path difference inside the film. So I've got to change my wavelength to match inside the film. Okay? And so here's, I've showed you just briefly, here's some practical examples of using it, and it works really nicely actually. Let me stop that there. Whoa, 58, man. I stopped with 70 seconds to go.